So what causes that, right? I have this charged rod here. Whoops. Pull it out here a little bit, right? And I haven't touched this thing, so the can is clearly neutral, right? And yet when I put the pipe near it, which has been charged up, it clearly attracts the pipe. The pipe clearly attracts the can, right? And so the way we can think of this is that my piece of PVC here is a charged rod, and it charges negative, I think, when it's rubbed. It doesn't matter, but we'll say it's charged negative. Now I've got my can over here. This is Dr. P. Because charges are free to move on this can, the negative charge here repels the electrons that are free to move and leaves a net positive charge on this side. So in a conductor, the charges are free to move away, and so they do, and now these positive charges are closer than the charges that repel, and so these guys are attracting the can to the PVC, and these guys are repelling the PVC pipe, but these guys are farther away, and so since the force is K, Q, Q, Q1, Q2 over distance squared, the total net charge on here is 0, so there's equal numbers of positive charges acting on this as there are negative ones. And so the attractive force, the attractive force from these two guys and the repulsive force from these two guys have the same numerator, but they have different denominators. This is the distance for the positive charges, this is the distance for the negative charges. Since they have a bigger distance, these guys have a weaker repulsive force than attractive force. And the can is attracted. So a charged object like this one can attract an uncharged object by first polarizing it, separating the charges somewhat, the uncharged object, then exerting a stronger force on the nearer charges. This happens with atoms and molecules all the time. An ion can first polarizes another molecule and then attracts it in the same way. So we're going to talk a little bit about the electric field. The electric field is sort of the thing we think of as reaching through space and influencing other objects. If I put a charged particle somewhere, Q, then it'll act on another charged particle, I'll think of it a lowercase q, through the electric field. You're sort of familiar with this from thinking about gravity. If this is the Earth, we have this thing called little g, which points towards the center of the Earth everywhere. And little g near the surface of the Earth is 9.8 meters per second squared. But it really has a value anywhere. If the force of gravity from Newton's law of universal gravitation is big G times the mass of one object times the mass of the other object over the distance between their centers squared. If we're talking about the Earth, we can say, well, one of the objects is the Earth. This quantity, let's call it M2 just M, so mass of the Earth and mass of the object. This quantity near the Earth we call mg. And so G is just big G times the mass of the Earth over the distance between the distance from the center of the Earth you are squared. It's just this quantity without the m. And that means if you multiply the g by any mass, it tells you the force that object experiences. And so for the Earth, this is the value of little g. Near the surface of the Earth, when d is the radius of the Earth, this is equal to 9.8 meters per second squared. But out here somewhere, it has a smaller value. Maybe it's 8 meters per second squared. Where the International Space Station flies, I think it's like 9.3 meters per second squared, and so on. And so all you do is multiply g by the mass, and that gets you the gravitational force. So for the electric field, it's the same way, kind of. We say, look, the electric field due to an object is the electric field, we'll draw it as a vector, is the force per charge, in the same way that the gravitational field is the force of gravity per mass. You can write these as vectors, right? That's what we did just a second ago. And so this is our definition for electric field. For point charges, the force is equal to k q over the distance squared. Right, where I have two charges like I drew before, say, q and little q. I'm just kind of drawing this one as a larger charge, but it doesn't really matter. And so that means the electric field, which is F over Q, is KQ over D squared. And if you remember, this points toward or away from the charges depending on whether they're attractive or repulsive, so I don't want to neglect the vector, but I'll just set it aside for a second. This looks very similar to G is equal to GM over D squared, right? Like that. And so this is for a point charge. So this is the definition of the electric field here. It's the force per charge, and this is what it is for a point charge. And so I can say, look, so I can say, what is the magnitude of the electric field 3 centimeters from a charge Q equals 4 nanocoulombs, right? And that's equal to, Q is equal to 4 times 10 to the minus 9th coulombs. That's 10 to the minus 9th is nano, right? And so I can just say, well, the magnitude of the electric field is just KQ over D squared, which is 9 times 10 to the 9th Newton meter squared per coulomb squared. That's our K, right? Times 4 times 10 to the minus 9th coulombs divided by 0.03 meters squared, right? And so this is the 10 to the 9th and the 10 to the minus 9th cancel, and let's see, so this becomes 9 times 4. The coulombs cancels with one of the coulombs. The meters squared are going to cancel with meter squareds. My units are just going to be newtons per coulomb. And this 3 squared is 9, 0.03 squared is 9 times 10 to the minus 4. I've already canceled the meter squared units with the meter squareds in the numerator. My 9s cancel, and I get E is equal to 4 times 10 to the 4th newtons per coulomb. That's the magnitude of the electric field. So by definition, at any point in space, the electric field points in the direction a positive charge would move if placed there. And so if I have some positive charge Q, like I did, and this is 4 nanocoulombs, then Q is greater than 0, so it's positive. And so you can sort of see that at any point in space, the electric field would point away. Right? Because if I put a positive charge anywhere, it would be repelled by this guy. And so the electric field points in the direction a positive charge would go. And so this allows us to draw electric fields around objects. So we're going to talk about drawing electric fields and electric field lines, right? And so there are 2 ways to do it. So the first way, if I have some charge Q here, let's say it's greater than 0, right? Then I can draw arrows indicating the direction that the charge would go if placed at that point. So if I'm at the same distance, if this is a point charge, if I'm at the same distance for all these 4 points that I've indicated, then the field should be about the same, so these arrows should be about the same length. We notice that since this is a point charge that I'm looking at, we know that E is KQ over the distance squared, where D is how far I am away, right? And so like in this case, that would be my D. Right, as I get farther away, since Q is staying the same, I'm still talking about the same charge, whose electric field I'm interested in. As I get farther away, I draw shorter arrows because the field gets weaker because D is getting larger and K and Q aren't changing. And so if I was going to draw this, this field, I might put bigger arrows near, and then as I got farther away, I would draw smaller and smaller arrows, always pointing away from Q, right? Because I know that that's the way the field points. And so that's how you can draw your electric field with vectors. The strength of the field is indicated by the length of the arrow, and its direction is indicated by which way the arrow is pointing. So the other way is continuous lines. So continuous lines, so for this method of drawing electric fields, rather than arrows, we can use continuous lines. The field direction at a point is tangent to the line there, and its magnitude depends on the line density. And so if I go back and draw my Q again, right, so rather than having separate arrows like this, I can draw continuous lines, and then I can say that the field at some point like here is along the direction of this line, tangent to this line at this point, which is still along the line. And its strength depends on the density of lines here. And you can see as I get farther and farther away, the density of lines decreases. Density of lines is higher here, but it's smaller out here. And so it portrays the same information as the previous approach, the vector approach, only slightly differently. There are a couple of more things here. So So we can indicate the relative magnitude of two charges by the number of field lines emanating. And so I can say, for example, I can say, look, I've got charge Q1 and charge Q2. And Q1 has, say, 4 lines emanating from it. But Q2 has so I can, this could be like a 5 nanocoulomb or a 8 nanocoulomb, and this could be a 4 nanocoulomb. And so I can indicate that drawing-wise by the number of lines that are emanating from the charges. So let's talk about properties of electric field lines for a minute. We've talked about the lines already a little bit. Electric field lines begin on positive charges and end on negative charges or an infinity. So if I just want to draw a positive charge, say Q greater than 0, I would just draw some outward lines this way, right? If I wanted to draw a negative charge, Q less than 0, I would draw some lines coming in, right? These obviously would have to be beginning on positive charges somehow. So let me draw a few more here on this guy, right? Like that. At any point in space, the field points in the direction a positive charge would go. And so if I were to put a charge here, the charge would go that way, right? And so the field points that way. I could, if I'm talking about this guy, if I put a charge over here, the field points that way, the positive charge will go this way. These are consistent remarks, right? If I put a little test charge Q here, it's going to be repelled by this guy. And so it's going to move away. The field points in the direction a positive charge would move. Same thing here. If this is a little test charge Q greater than 0, it's going to move towards this negative charge that's nearby. The number of lines entering or leaving a charge indicates its magnitude. So notice this guy has 8 lines coming in, and this guy has 4 lines going out. And so if I called this Q1 and Q2, I could say the magnitude of Q2 is equal to twice the magnitude of Q1. Right? We already said a minute ago that step 4, which is the strength of the field, the magnitude of the field, is proportional to the density of the lines. And so I can just, you know, there could be some lines like this, just some electric field lines in space caused by some distribution of charges somewhere. And I can say, look, this region is where the field is the strongest. Out here it's weaker. All right, low density of lines, high density of lines. So the field is tangent to the line, so if I have a line like this, we talked about this before, it points that way there, whereas it points this way down here. That's the direction of the electric field at that point. Number 6 is field lines cannot cross, and you can sort of see why, right? If the field lines point in the direction a positive charge will go, if they cross, where would a charge go if placed at the place where they cross, right? And so instead what you would see there is this and this maybe. So it looked like they cross, but they don't really cross. All right, that's a little discussion of the properties of field lines. So let me give an example or two. The first example, I'll say, look, we have two charges. One of them is positive and one of them is negative. So Q2 is positive, Q1 is negative, and they have the same magnitude, right? You can say 4 and minus 4 microcoulombs, but you can pick any equal numbers, right? And I'd say, well, let's just draw them here. Here's Q1, that's less than 0, and here's Q2, it's greater than 0, right? And now I can just start asking what the field does in the places in between. Well, a positive charge placed between them would just move in this direction. It would be repelled by this guy, and it would be attracted by this guy. And so we can say, look, the electric field between them looks like that. So then I can ask a question, well, what does it look like at any point along the halfway line between them? Right? And I can say so let's say what the field looks like up here. Well, this guy's repelling, right? But this guy's attracting with an equal force, and so the net effect is this way, right? A positive charge placed at this point would be repelled by this guy and attracted by this guy equally. And so the electric field in between, no matter where I pick it, is going to point sort of horizontal, right? Right at the center line, right? If I pick a point that's more towards this guy, it'll be more attracted than it is repelled. So let's say I pick a point like here, right? This guy's got a stronger repulsive force than this guy has an attractive force. This guy's pushing him away, this guy's pulling him in. Maybe the net effect is like that. Try to make that a straight line, right? And so on. So at these points I see this, and so what I see is instead of just radial lines going in towards this guy and out from this guy, I see lines that get bent. And so my electric field lines look like this. Something like that. Right. You could do a similar thing with two equal positive charges. Suppose instead of this drawing, I do this one. I say Q1 and Q2 both greater than 0, right? And now I draw them here. Here's Q1, and here's Q2. So now, since they have the same magnitude, the field halfway between them is 0, right? So let's pick right here, right? The field on this side, if you put a positive charge anywhere on this side, it'll go that way. If you put a positive charge anywhere on this half, it'll go that way. And if you manage to get one dead center, it'll just sit there, right? So you might have a field that looks like that. Suppose you put a charge here, right? Well, this one's going to push it that way, and this one's going to push it that way. And so the net effect is up, right? And so you get a field going this way. Same way down here. In fact, anywhere along this line, you get an upward push. Well, what happens a little bit to this side, right? A little bit to this side, this guy's pushing this way, and this guy's got a smaller push going that way. And so the net effect is kind of like that. And so what you see on these guys they're kind of repelling each other. That type of thing. I could draw a few more in here, right? Like that. So there are lots of examples of these. You can see them in your book or on the web. It gets a little more complicated when you have different numbers. Now, I tried to draw roughly the same number of lines. If you have different numbers of charges, if one of them is stronger than the other, then this thing gets asymmetric and it gets more complicated to draw.